Succeeding, we have David Caldwell joining us from Australia. David is Vice President of Artificial Intelligence and Machine Learning at Tricentis. He has been in the industry for 13 years and running AI teams for the last 4 years. He believes that by unifying the rigorous practices of software engineering with the emerging discipline of machine learning, we can accelerate both. He has a track record of creating innovative solutions to meet customer and internal stakeholder requirements. His expertise in AI is focused on areas of quality assurance, test automation, test practice, and development. Today, David will share a presentation about testing an AI and testing with AI going beyond the validation data. Welcome, David. Over to you.
Thank you very much, Eric, and thank you to everyone that's made the time to attend. My name is Dave. I'll be doing a bit of an introduction to myself in the next 2 slides before we jump into the topic. But first, thank you everyone that's been able to make it. Please feel free to type anything that you have in terms of questions into the participants' questions section. I love taking the questions, and some of them we may even answer live during the session. So again, thank you all for coming, and let's get cracking. So today we're going to be covering off a novel story of a research program where we developed an artificial intelligence solution using deep neural networks to solve a problem that popped up in the world of software testing. We're going to be covering off this journey in about 5 phases: the intransigent problem, the novel solution, the first couple of failures, and there were a fair few that we had, the eventual success, and finally what we learned, so that you can take these lessons and apply them either in your own machine learning journeys or just in terms of education to take back to your teams if you have machine learning people or data scientists in your teams. But before I jump into the presentation, I thought it would be good to give you a little bit of background information about me. I live in Sydney, Australia, if you can't tell from the horrendously ochre accent. I've been in the world of software testing and software engineering and development for about 14 years. I'm currently the Vice President of Artificial Intelligence and Machine Learning at Tricentis, which is a tech company worth about $2 billion, founded out of the US. And I've been running AI and machine learning there for the last 4.5 years now. But that's sort of my work history. Sort of more interestingly, I'm a father of 5 children, as you can see here on the right-hand side of the screen. They definitely keep me, I would say, more busy than my work. And if you see a small head pop through and appear here, I'm sorry, there's not much I can do about it. Please tolerate those. And I'm the husband of 1 lovely wife. In my spare time, when I'm not trying to cut machine learning code, I actually like to do things that are completely unrelated to the world of software testing, but related to my passion. My passion is building things, building new things. And so I like to get together with my children and we build projects. We build up in the top, you can see projects there made out of resin and wood. This one's a camphor table that we used as a benchtop in our kitchen. Great fun project for the kids to learn to get their hands onto something. And in a completely different vein, I also like to work with the kids to build boats. Down in the bottom, the kids are trying to help me paint one of these boats. Not the most precise painters. There was a little bit of cleanup needed, but the final result, you can see down the bottom right there. All of these things, these hobbies, very much connect back to my main passion, which is taking nothing and trying to get something, to construct something out of it. It's the whole reason I got into the world of software engineering, and it's one of the reasons why I find machine learning and artificial intelligence so fascinating. So let's get into the actual topic. We're going to be structuring this topic and in a way that many of you will be familiar with if you've ever seen a Marvel movie, or I think really any movie made after 1950. And that is, we're going to cover off the hero's journey. The hero's journey is, I think, as old as the Iliad. It's an extremely old storytelling approach. And unlike most storytellers, I'm actually going to tell you how I'm going to tell the story because it's important. We're going to go through the initial journey of understanding what the problem is that we've got. What is, software testing? Because many of you probably haven't seen that industry or worked in it before. What are the problems that face that industry? And how did machine learning, and specifically artificial intelligence, enable us to get out of those problems? How did we tackle them? How did we overcome the challenges that we face there? And what value does that bring? So let's jump into it. Let's start the adventure with a little bit of information. What is software testing? At its core, it's relatively simple. You have a process that's used to validate that software is ready for release and of a high quality. And that's kind of it. A lot of the rest of everything else sort of floats around the edges of that concept. You've got a requirement. This is something that you need to build. It's a document or a statement or a Jira ticket or one of these post-it notes that I've got up on my wall. These are the requirements. And then you've got a solution. This could be code. It could be a machine learning model. It could be a config or a product you buy off the shelf. Then you test it. You do the validation. And that either results in a product that's ready to go or it results in bugs. An analogy for software testing would be renovations. Something else that I'm sorry to say I've had a bit of experience in recently, and I'm sure some of you will have been in the same boat when you want to renovate or remodel your house. You start out by having a lot of dreams, the wonderful things you're going to do. I recently thought it'd be great to tear out the kitchen. And that was my requirement, was I want this whole place to be open plan. And so you start drawing up those plans. That's the requirements phase of a software project. And you're starting to build out those requirements and specify what is it that I need to construct. And then you go over to the contractors, the builders, the whatever they're called in your country. And you give them that spec. You give them the requirement, say, okay, time to build this house. And sure, you come back and it's all done. Well, that's kind of how I thought it worked. That's not how it actually works. You come back throughout the time and you find on these various walkthroughs that there's some things that aren't quite right. Like the shower's not aligned, the toilet doesn't work, the floors aren't level, the walls have been painted the wrong color. These are like the bugs. And after you've gone through and you've resolved all these bugs, you move in. So software testing is like doing that walkthrough of the house. You've got what you think you need and you're going through and you're checking it. So far, so good, right? Not really any problems. And it operated relatively fine with people doing software testing manually, like going through and actually using the application. Someone would ship a product, a bunch of people, usually the users of that product, the people that were going to live in the proverbial house, would come in and they would use the product. They'd try it out, play around with it and say, cool, I validate this product works, tick it off. And it would all be done by hand, by human labor using those products. But there was a challenge. As the software technology world started to advance and as it became easier and easier to ship apps rapidly, we started to see the cracks in this technique. This was where the cloud and cloud deployments and cloud availability started to make it really, really easy to just get that change right out there, to take it from an idea through to the build and then drop it into production as quick as possible. And this is where we started to see the elite. These are the groups of people that, or the groups of companies that are right at the cutting edge and the forefront of technology. They were no longer thinking, all right, we ship changes through to production once every 3 months or once every half year, which was more common sort of back in 2014, 15. They were now saying, no, we want to ship these changes every week, every day, every hour. Companies like Amazon were starting to get famous for saying, yeah, we ship thousands of changes to production every single day. And that's a problem. The problem was that those humans that were going in and validating it, that were trying to do these checks, were now too slow. These people could no longer be part of that process. And especially as the checks got larger and larger, as the number of validations you needed to do grew, the time that it took grew as well. So, all right, there's a solution for that. We know that testing is the problem, and we actually found a lot of studies. This was a common trend from 2017 all the way through till current, actually, that people would say, if we want to innovate in software delivery, the number one thing impeding us is this testing, the manual effort it takes to validate the app. And so everyone reached for test automation. This was robots, teaching a robot to use the application. And the robot would do checks along the way. It would say, tick these things off and make sure they work. This is somewhat akin to automated tests in your AI and ML models would be your validation or training in datasets. These are the things that while you're training your model, they go through and they say, are you actually progressing? Are you increasing your value? In software test automation, these would be checks that would go in and say, I want to log into the app and I'm going to validate that I can create a transaction and that the transaction amount is correct. Those were now being automated by robots. So they're done and they're fast and they no longer require human effort. So we've solved the problem. Or did we? So now we're shipping once a day, thousands of times a day, potentially for larger companies. And we've got large volumes of these tests that are being run by robots. And it happens that the robots are not very good at adapting to change because the robots are scripted. They're not learning. They're just going through and saying, do A, B, C, D, E, and check F. But you're changing your app. That's the whole point of throwing all of these tests, all of these changes into prod, is to actually change your app. And so Google released a study that showed even when you've got very high degrees of automation, most of the time these tests are going to start to fail, and they're not going to start to fail because they've found a bug. They're going to start to fail just because these tests are detecting changes in the app that are irrelevant, or because the tests are fragile. They'll be detecting irrelevant changes, like you might have changed the color of a button and the test will go, nope, it's done, sorry. So we ended up with this problem where we'd now built lots of these tests, lots of these automated robotic validations. They were very static and they weren't learning, and they were a bit like smoke detectors. A good smoke detector goes off when your house is on fire. Now, everyone in this virtual summit has probably had a smoke detector that goes off when your house is not on fire. Usually it's because it's a bit too close to the toaster or too close to the oven or something like that. And it's going to say, hey, we detected smoke coming out of the oven. This is what a flaky test is like. This is what one of those robotic tests is like that's failing for the wrong reason. This is what happens when your tests are unable to learn. And the result of that is often the same result that a smoke detector that's going off at 3 a.m. gets. If it's lucky, it gets its battery removed, which is kind of like throwing the test away. This photo here was not one of my smoke detectors, but I have seen other smoke detectors meet a similar fate. This is the fate of the flaky test, the test that cannot learn, the test that cannot adapt. And so now we've completed the first arc of that hero's journey. We've had the solution. We thought we had ways of solving that problem that we originally had, and we've realized that those solutions, those automation, are not good enough. We need to extend the state of the art, and we need to do it using techniques that do not exist. This is where we started to go beyond the world of functional, logical, algorithmic programming and reach out into machine learning. And so at Tricentis, we looked at this problem and we thought, is there an existing way that this problem is being solved in other areas? Is there a way where adapting to the environment is being dealt with? And the closest analogy we could come with was self-driving cars. So we took some of the technology that was being put in self-driving cars, specifically things like deep convolutional neural networks, object detectors, and the like. And we said, well, can we adapt this technology, these object detectors? And this example was one of the earlier forms of research. We were using a YOLO v3 network, but we actually ended up evolving that into a network that we took out a patent on that had a very high degree of accuracy. And we said, can we step away from these tests being very fragile tests that are machines that don't know how to understand the environment they're operating in? And can we teach machines to see and to act like humans by teaching them how these applications hang together using neural networks? So instead of taking in a form or an image or something like that and just seeing pixels or technology or HTML elements or whatever it might be that it's seeing, can we show it that presentation and teach it that these are drop downs and buttons and inputs and tables? Can we teach it to see these applications in the same way that a human would? Because if we can do that, then we can teach it to act like a human would. So that was our original kind of exciting moment. We got to this in 2018. We said, yes, this is definitely doable. And then we immediately said, well, what do you do when you've got an idea? Well, you straight away take it and you start prototyping it. You build a machine learning model. And we called this machine learning model Neo. We've built a data set because the data sets for this don't actually exist on the internet. So we needed to get it constructed and labeled. And a lot of the learnings that we actually encountered were around how do you actually make these data sets and how do you label them correctly? And we were able to get a degree of accuracy. But as you can see in this example, like the top is the raw video, the bottom is the AI trying to observe what the human's doing and track the activities that the human was doing. And you can see in that there is actually a fairly high degree of overprediction, a fairly high degree of inaccuracy. And that was quite disappointing because it was a reasonably large data set that we trained it on. And we noticed that no matter how many different models we used, I think, 6 different generations of architectures from RCNNs to single shot detectors and YOLO networks, all these other different forms of deep convolutional neural network that were the state of the art at the time. And you can see here by our loss graph that we were completely unable to get it to converge at anywhere near the level of accuracy that we wanted. And there was an incredibly high degree of over prediction here. And you can see that because if you look on this image that's on the right-hand side of this screen, there's a whole bunch of controls of bounding boxes being predicted where there's actually nothing there. So we thought about this and we said, okay, we've had an idea, but this idea is not really panning out. We can now go one of 2 ways. We either acknowledge this probably won't work, or we can press on. We decided to press on. It took a while, and there was not one solution to this. There was actually about 5 different solutions that we needed to apply to take it from where we were to where we needed to be. And in, I guess, what will be a twist in the AI world, only one of those solutions was to increase the size of the data pool. So the first thing that we tried was we measured our MAP to see where we were at. And the MAP was rather awful. It was at 31.4. And then we thought, okay, well, this is obviously just a data set problem. We just need to collect more data, make sure that we've got the right data, make sure that it's representative, go source additional data. So we took the data set size that we were using for training from 150,000 samples to 800,000 samples. So a significant increase in the size of the data set pool. And this is, by the way, transfer learning. So we'd already been using a model that was pre-trained on ImageNet and Pascal VOC for object detection. And we were a bit disappointed with the results that we got back out of it. We went from 31.4 MAP to 36.1, which was not awful for the time, this being back in sort of 2018, but we were still seeing a very high degree of over prediction, so that was a low precision, whereas the recall was okay. And it took us quite a while of analyzing this data to understand exactly why. We've been sourcing a lot of this data from video feeds that we've been retrieving from usage samples of people using real-world applications. However, because we were doing transfer learning between a real-world data set, which was ImageNet, and a data set which was inherently machine generated, which was pictures of user interfaces, the features that were being learned in the ImageNet were mostly useless to the transfer learned dataset. They were able to give it a bit of a jump start, but not much. So we said, okay, well, maybe what we need to do here is we need to increase the amount of data augmentation we're doing and come up with some additional ways. So we tried mosaics and random cropping, jitter, we used color matching, we used all different forms of data augmentation we could get. And that was all right. Same data set, the 800,000, we went from 36.1 to 42.7. Still not where we needed to be. Our target for this was at 48. And we still weren't there with an increased size data set and with data augmentation now added to our training pipeline. And this was disappointing. It was almost at that point, actually, that we decided we would kill the project. But luckily, we hired a couple of additional people that weren't in machine learning. These were just software engineers that knew a lot about computer vision. And they brought in an idea for how we could use the existing data we had and genetic algorithms to just create additional examples of data by pairing together different controls and parts of the labeled data set and creating new forms, new screens out of it. It was mimicking different design syntaxes to try to generate not just randomized synthetic data, but semi-naturalized synthetic data. And they used the lowlights, the data that was worst predicted, as some of the highest indicators when generating the synthetic data. So without adding any natural data, so no additional data labeling costs, and without changing our data augmentation techniques, just by adding synthetic data to the natural data that was algorithmically generated, we were able to go from 42.7 MAP to 48.1, which was just a hair over where our target was for being able to productionize it. And that was an amazing outcome. It really hammered home to us the value that you get out of examining the data that you have and reasoning about it, trying to figure out why the data is the way it is and looking at it from an engineering perspective and not just from a data scientific perspective of saying what are the numbers and what are the stats and how do you arrange the data. So that synthetic data generation technique got us over the line. However, one of the machine learning engineers was then able to make some breakthroughs in the architecture of the neural network, which significantly reduced the amount of gradient loss that we had propagating throughout the network. And that was able to bump us up again from 48.1 to 52. So we exceeded our target for mean average precision. And the only way that we were able to do that was by combining the two sets of skills, the people that knew how machine learning and data science worked with the strong mathematical and scientific background, and the engineering people that were able to examine the problems with a more algorithmic outlook on life and design our engineered solutions to try to get us to the answer we needed, which in this case was a larger data set of naturalized data. So we got to our target. We still needed to build this into a product. So we took that solution and we started asking it, can it track when a human is using an application? Can it, now that it's got a bit better precision, actually the precision on this was off the charts. It still had some issues with sizing, but we were able to correct those with an engineering solution. And it was able to completely follow a user's activities as they used an application and spit out the actions that they took just by observing this video feed of somebody doing something. Just by watching them perform actions on an application, They were able to spit out the process, the data, everything that it was that they used. And this was the breakthrough that allowed us to go from this is a cool toy to something that we can actually develop into a product. And that product needed one more thing. Understanding the layout of the application was nothing without being able to understand the text. The text in applications is the data of the application. So one of the machine learning engineers paired up with one of the computer vision engineers and designed a single shot OCR network, which was a breakthrough in the area of optical character recognition, where most of the networks at the time were offering fairly low accuracy on a very high gradient. We were able to achieve the 1080p image on CPU processing with our neural network in 38 milliseconds, where the current industry benchmark at the time was 152. So now we've got two neural networks that can understand the layout of the application and the controls and the data and the text within it. We used those and paired them together to say, now let's tackle that original problem, that test automation problem. We've built this AI, we've built this machine learning solution that is able to observe and track and act like a human. It can understand the application like a human. It now can adapt when the application changes. It does not need to be fragile. It can say, all right, this app, now one of the buttons has changed, a label is different, or it's moved, or whatever the change may be. It acts with a degree of confidence autonomously from the actual script that you give it. And we built this machine learning product into a solution that we called Vision AI. And Vision AI, because we'd spent that time doing the machine learning research and tackling the really difficult problems, we were able to offer capabilities that no one else could, because the underlying technology that we had was truly unique. So this allowed us to do things like say, hey, you're a tester, you want to build an automated test. You don't need to wait for that app to be ready. You can draw what the app is going to look like on a whiteboard, take a photo of it, and send that to the AI, and it will go, cool, this looks like a user interface. I know how to use it. You can build your test before the app is even present. A complete breakthrough in the industry that was only enabled because of that persistence in driving through, in researching, in machine learning. We currently have over 800 enterprise customers using this Vision AI product, and it's running over 1.5 million tests every month. So now we've almost kind of completed that hero's journey arc. We've gone right from the bottom where we thought this is an intransigent problem that we can't solve. We've found the enlightenment, we've learned what we needed to learn, and we're almost there. This is the phase in the movie where the person, the hero, has just sort of come back up out of the final battle, and it's almost like an older and a wiser protagonist has emerged. And that really was what it felt like going through this full research cycle, being able to see from the problem to the original hope that you had that the solution would be there, and it was so easy because machine learning, you just point and click with the data, to finding all the challenges and pushing through them and overcoming them. At the end of it, we felt like we would do it all again, but we would do it all differently. And there was three things that my research team kind of gave me as a feedback after this project. And the first of these three things was we have to be a bit careful what we research. We spent a lot of time researching the optical character recognition component of that. And optical character recognition was not a novel problem. We were just trying to make it faster. If we did this again, this is advice that I give to every company that's out there that looks at us and says, well, you do original machine learning research and you've turned it into a successful product. We've got all these ideas we want to use machine learning for. And my first piece of advice is, if you can, buy a solution for it, because original research is incredibly time consuming, it is difficult, and it is painful. And if you can find a solution that's out there on the market, then it's much better to buy that solution, integrate it, and see if you get the value out of it really early on. And then if you believe that you can turn this into a market differentiator for your company, research that differentiator. But solve the problem first by using something that exists, and then research from there on. That's the first thing. Our OCR network, we would not have researched up front. We would have purchased a solution for that. The second thing is more data is okay, but different data is awesome. We thought that by increasing the data pool size, we would drastically improve the accuracy of our machine learning models. But we'd fallen prey to one of the classic blunders, to quote the Princess Bride. And that was that we were just sort of adding more of a similar data type to the stack. And it wasn't increasing the diversity of that stack. And so by introducing synthetic data and by introducing data augmentation, and by pushing away from just increasing the amount of data and increasing, therefore, the time of the training runs and everything else that goes along with it, and approaching it as an engineering problem that needs to be solved and saying, how can we force this data to be different? Is there an algorithm that we can use to mutate this data and experiment with this data to see if we can turn it into something different that will allow us to get better accuracy results? Then that was where our breakthroughs occurred. We achieved more progress in the 2 weeks it took us to generate the first of the synthetic data creation algorithms than the 3 months worth of data labeling effort that we undertook to increase the size of the data set. So that's probably one of the learnings that we would say is approach your data as a engineering problem with an engineering solution, and look for ways to increase diversity in the data more than trying to increase volume in the data. And the final thing is, it is difficult, but at the end of the day, persistence pays off in machine learning in a way that it doesn't pay off in many other software endeavors. In traditional software construction, if you meet a difficult problem, it's very often a good idea to pivot and try to find an easier way to solve it. In machine learning, you're kind of already operating at the bleeding edge of technology. So it's often the case that if you can push through and find that breakthrough, then you will be able to offer something that's not just good, but something that is unique. And something that is unique allows you to be first in market and take advantage of a place that no one is, and get that leader status and really push through. So those are the 3 things that we learned doing novel machine learning in testing, and I hope they're of some use to you. That's the last slide that I had, so I think we've got time for some questions. All right, there is quite a few of them here, actually. Go ahead.
Thank you for that great talk. It is always great to have someone that is at the cutting edge of this technology to share his vision of what the future what the future of machine learning holds, right? Now, I hope the audience has submitted great questions for David. Yet, before going to that, I actually have a question for you, David, to warm up. AI software testing protocols can go even further using so-called self-healing. This refers to the process when the algorithm identifies changes in the application and automatically adapts to remain functional. This saves time in test maintenance, which is why some people have called it automation for test automation. What are some of the challenges in implementing self-healing tests?
That's a really good question, and it's actually going to link into a question that's been asked in the chat by Roia as well. When we implemented these self-healing algorithms, you're giving the AI a certain amount of autonomy in action. You're saying, when you come into a problem, you make a decision, but you don't then just present that decision back to a human who's going to assess that decision. You actually act on that decision and then notify the human after the fact. And this puts you into a little bit of a dangerous realm in AI usage, which is where you've removed the human from the decision-making loop. And as soon as you do that, then you start to have challenges with being able to explain why the AI took a particular decision, why it was able to create certain pathways. And the reason this links really neatly into one of the questions in the chat, this was by Rawia Hamza, says, while presenting your neural net models, were you asked about the model's explainability? Explainability in artificial intelligence becomes exponentially more important when the artificial intelligence is starting to make decisions autonomously. So yes, we actually have to build explainability into these neural networks. So we're using some of the open source explainability tooling so that when the AI takes a decision, such as saying, I'm going to self-heal, I'm going to take this path instead of that path, it can actually tell you why it took one path and not the other. Because otherwise, when a human comes back to review the decision, which has already been made, by the way, it's not like you can go back and unmake it, they're able to see why that decision was made, and they can accept that decision, or they can challenge it and raise a defect and say, well, hang on, I need to go and notify that this decision was wrong and because the reasoning is wrong. So interpretability and explainability of artificial intelligence is critically important as soon as you allow the artificial intelligence to act with the human out of the loop. All right, there's another... Sorry, do you mind if I take the next question here, Eric?
Ahead, we have some time. You can pick up some questions, and then later on we can choose which one of all those questions do you think is the most relevant or the most interesting, so we can prize that person. What do you think?
I think that's a good idea. So there's a very good question here by Edu Gomez, and it says, what are some of the challenges involved in testing AI systems? The biggest challenge in testing AI systems is the lie that the number you put out as your requirement, because remember back to the beginning of the talk, we talked about how the requirement and then the solution and then the validation. Validation can't happen without the requirement. In neural nets and AI, we often say that the requirement is the accuracy number or the F1 score or MAP or whatever it was. We did this too. We said MAP of 48 was our requirement. And the lie that we tell ourselves is number better, result better. And the reason that's a lie is because when you're dealing with deep neural nets or really any sufficiently complex data, you need to start looking into the intersections of the variables to discover if the overall improvement has caused some localized regression. I'll give you an example here that's actually more from the finance industry, because we build artificial intelligence and we do testing systems. So we often get asked to consult with companies that are trying to implement AI systems into their production environments. And for one of these financial services companies, they were trying to use their AI for what's actually a fairly simple task from a machine learning point of view. It was just doing a regression. It was predicting the likelihood of an outcome from a 0 to 1. And in this case, it was trying to predict the likelihood of somebody being eligible for a certain degree of credit rating. And it was accurate and it met all of its goals. So that there's a certain set of interpretability goals that you've got to meet, and there's a certain compliance set of goals that you've got to meet, showing that you have the right level of accuracy for the different categories of gender and all the different protected characteristics that exist. At least this is under Australian law. And so they put those in there as their requirements, and they ticked them all off, and they said, yes, we're good to go. And we challenged it. We said, well, actually, let's start looking into the intersections a bit. And what we mean by the intersections is, let's say, for example, that overall, your AI has a high accuracy for females, a high accuracy for males. However, it has a low accuracy for females over 65. That could be a problem because you could be starting to breach some of the discrimination rules. So testing an AI is much less about what are the what are the list of requirements that I have. And it's actually far more of a collaborative exploratory exercise in trying to find holes in the system by looking at where these things intersect and trying to find where the numbers dip, looking at confusion matrices and saying, yeah, this is a problem. All right, we've got 1 minute to jump on the winning question. Okay. Oh, that's a hard one. Let me grab a couple of these.
Take your time. There are a few questions there, so take your time. You can go and read through them.
All right. Of all the ones I've read through so far, I think the best question, it's technically not a question, it's a request for comment, but it hides within it some good knowledge. And that's from Praveen Natarajan. And it says, could you please shed some light on generating effective counterfactual examples if we're going to test the robustness of the machine learning model? So this was actually what we did when we were generating the synthetic test data. We needed to be able to, first off, detect areas where the AI was dipping, where it didn't actually have good detection. Because the AI over time starts adapting to whatever data you start feeding it in. So if you generate a set of counterfactual examples and then you redo the training, you'll often find that the counterfactual examples you generate have been adapted to, and it's now quite good at dealing with them. So we found that the best way to do the counterfactual example and sample generation was to remove the the synthetic data from the training pipeline every period. We had 5 epochs was our period, but the number's somewhat irrelevant. And insert back in another set of counterfactual examples that have been generated dynamically as the training was occurring, so that you're trying to make the model adapt better to the areas where it is starting to go into local minima. And doing that is how we were able to push our MAP much higher, because you were able to not just find 1 or 2 counterfacts and start them straight away. You would be adapting your counterfacts as the training continued, and you'd be forcing the model to generalize in a much more effective way. So I thought that was a very good question, and it showed a lot of insight. So Praveen, well done.
We have a winner. Please share your email and we will be sending the prize. Thank you very much for sending that comment, that question. And well, time is short and I enjoyed so much your talk, David. Thank you so much for your time and your effort in preparing this, right? We hope that you can join us for the next event and share more of your knowledge. To the audience, don't forget we have a networking lounge where you can share your opinions with other enthusiasts. And stay tuned. We are coming back with our next session in just a few minutes. David, thank you very much.
Yeah.